Imagine hurling a baseball so hard that it not only escapes Earth's gravity, but visits 4 different planets before flying into the depths of space forever. Sounds impossible, right? Well, that's exactly what NASA accomplished in 1977 with Voyager 2, and the precision required was so mind-boggling that missing by just a few kilometers or seconds would have meant complete mission failure. Today, we're diving into one of the most incredible feats of engineering and mathematics ever attempted, how a spacecraft the size of a small car managed to thread the needle through our solar system with surgical precision. Picture this. You're standing on a moving train, trying to throw a dart at a bullseye on another moving train while both trains are racing through a tunnel at breakneck speed. Now multiply that difficulty by about 1 trillion, and you're getting close to understanding the challenge NASA faced. Voyager 2 had to navigate through the gravitational chaos of our solar system, using the planets themselves as stepping stones to gain speed and change direction, all while those planets were hurtling through space at thousands of miles per hour. The story begins with the cosmic lottery ticket, a planetary alignment that happens once every 175 years. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune were positioned in such a way that a single spacecraft could potentially visit all 4 gas giants using what's called gravitational slingshots. It was like finding 4 perfect dominoes lined up in space, waiting to give our little probe the boost it needed to reach the edge of our solar system. But here's where things get absolutely insane. To reach the first domino, Jupiter Voyager 2 needed to escape Earth's gravitational grip entirely. The Sun's gravity creates what scientists describe as a massive invisible well in space, and Earth sits partway down that well, constantly falling but never hitting bottom because of our sideways motion. For Voyager to climb out of this well and reach Jupiter, it needed to achieve an escape velocity of 42 kilometers per second. That's fast enough to circle the entire Earth in just under 20 minutes. The problem was that no rocket in 1977 was powerful enough to directly accelerate Voyager to that speed. So NASA engineers came up with a brilliant workaround. Earth was already racing around the Sun at 30 kilometers per second, so they decided to use Earth's own motion as a head start. By launching Voyager in the same direction Earth was traveling, they essentially gave the spacecraft a running start of 30 kilometers per second before the rocket even fired. Think of it like jumping off a moving train. If you jump forward, you add your jumping speed to the train's speed. If you jump backward, you subtract it. NASA chose to jump forward, but even with this cosmic boost, the precision required was absolutely staggering. Here's where the needle-threading metaphor becomes literal. To reach Jupiter at exactly the right time and place for a gravitational assist, Voyager 2 had to pass through a corridor in space that was only 150 kilometers wide. To put that in perspective, imagine trying to throw a grain of rice through a wedding ring from a distance of 50 miles while both you and the ring are moving at different speeds. Miss that corridor by even a fraction, and Voyager would sail past Jupiter without getting the speed boost it desperately needed. The navigation challenge was unlike anything attempted before. NASA engineers had to predict where Jupiter would be 18 months in the future, account for the gravitational pull of every major object in the solar system, and plot a trajectory that would thread that impossibly narrow corridor. They were essentially playing 3-dimensional billiards with planets as balls and gravity as the table. To make course corrections along the way, Voyager 2 was equipped with 5 sets of tiny thrusters positioned around its body. These thrusters could rotate the spacecraft around all 3 axes. Imagine spinning a coin while it's flying through the air, but with computer-controlled precision. Each thruster burn had to be calculated down to fractions of a second, because in space, even a tiny push in the wrong direction can send you millions of miles off course. But how do you know where you are in the vastness of space? GPS doesn't work when you're halfway to Jupiter. NASA solved this by using something called the Deep Space Network, a system of massive radio dishes on Earth that could ping Voyager and measure how long the signal took to return. By timing these radio signals and accounting for the Doppler shift as Voyager moved, they could determine the spacecraft's exact position and speed with incredible accuracy. The math involved was so complex that it pushed 1970s computers to their absolute limits. Every gravitational influence had to be calculated, not just from the major planets, but from moons, asteroids, and even the subtle effects of solar radiation pressure pushing against Voyager's surfaces. It was like trying to predict the exact path of a feather falling through a hurricane while accounting for every gust of wind. As launch day approached in August 1977, the pressure was immense. The planetary alignment window was closing, and if they missed it, humanity would have to wait another 175 years for the same opportunity. The Titan Centaur rocket that would carry Voyager into space had never attempted such an ambitious trajectory, and failure meant losing one of the most expensive and sophisticated robots ever built. Launch was perfect, but that was just the beginning. Over the following months, as Voyager 2 coasted toward its Jupiter encounter, NASA engineers monitored every aspect of its journey. They tracked its position daily, made tiny course corrections when needed, and held their breath as the spacecraft approached the critical moment. When Voyager 2 finally reached Jupiter in July 1979, the results were nothing short of miraculous. After traveling over 400 million miles through space, navigating gravitational fields that could have torn it apart or flung it into the sun, Voyager arrived at its target point just 1.4 seconds late and only 60 kilometers off course. To put that in perspective, it's like throwing a dart from New York to Los Angeles and hitting within a few inches of the bullseye. The Jupiter flyby was spectacular, but it was also just the first domino. As Voyager approached the giant planet, Jupiter's immense gravity grabbed hold of the spacecraft and accelerated it like a cosmic slingshot. The spacecraft's speed increased dramatically as it fell into Jupiter's gravitational well, swung around the planet, and then shot back out with enough velocity to reach Saturn. But here's the really mind-bending part. Engineers had to calculate not just where Jupiter was, but where Saturn would be when Voyager got there, and then where Uranus would be for the next encounter, and finally where Neptune would be for the grand finale. Each gravity assist had to be perfectly timed and positioned to set up the next one. It was like planning a series of trick shots in cosmic pool, where each shot has to set up the next one across a table the size of the solar system. The precision required for each planetary encounter was extraordinary. At Jupiter, Voyager had to pass within a specific distance range to get exactly the right amount of gravitational boost. Too close, and the intense radiation would fry the spacecraft's electronics. Too far, and it wouldn't gain enough speed to reach Saturn. The margin for error was essentially zero. As Voyager continued its journey, each subsequent encounter became even more challenging. The spacecraft was moving faster, the distances were greater, and any small error from previous encounters would compound over time. It's like trying to hit a moving target while riding a roller coaster, except the roller coaster is traveling at thousands of miles per hour and the target is millions of miles away. The engineering team had to constantly update their calculations as new data came in. They discovered that Jupiter was slightly more massive than previously thought, which meant Voyager's trajectory was subtly different than predicted. These tiny differences required course corrections that had to be calculated and executed with split-second timing. What makes this achievement even more remarkable is that it was accomplished with 1970s technology. The computer that guided Voyager 2 through its incredible journey had less processing power than a modern calculator. The engineers relied on slide rules, mechanical calculators, and early computers that filled entire rooms. They were essentially performing brain surgery with stone tools, and somehow they pulled it off flawlessly. The legacy of Voyager 2's needle-threading journey extends far beyond just visiting planets. The mission demonstrated that with enough precision, planning, and mathematical brilliance, humans could send robotic explorers to the farthest reaches of our solar system and beyond. It proved that the seemingly impossible was just a really difficult math problem waiting to be solved. Today, nearly 5 decades later, Voyager 2 is still traveling through interstellar space, sending back data from beyond the edge of our solar system. It threaded the needle so perfectly that it not only completed its primary mission, but continues to make discoveries in regions of space no human-made object had ever reached before. That incredible journey that began with such precise navigation through our solar system has become humanity's farthest-reaching ambassador to the cosmos.